In this example, I'm trying to show how to model erosion for the SAGD operations using Ashaw SemiDynamic Software. In the previous example, we show how to model SAGD with Ashaw software, but this example, we try to show how to use erosion module and considering the erosion effects on the flow control devices and histomatching it. Most FCDs are positive in SAGD operation. This is one of the ideal example of the flow control devices for the SAGD operation. We see the previous baseline and FCD deployment. We see the jump in the uplift, and mostly we see the uplift and better conformance using FCD along the producer, but there are cases that we see negative effect, and you see like the baseline is much higher than after the FCD deployment. And most of these concerns with the flow control devices are regarding the erosion. And they're mostly because we can't model erosion and using commercial softwares or whatever we're using for modeling. It's very complex phenomena, and now we have this module in Ashaw, which is, I think, unique using for SAGD and other applications. This example is just about SAGD. Most operators and surface companies using API 14E erosion equation, they're not really using it because it's a perfect predictions and it's modeling the complex mechanism of erosion. They're really using it because it's super simple. This is the equation. You just have a C constant, which is either 100 or 150, and you divide it by square root of the density of the mixture. And this is super simple, but it has a lot of limitations that we're going to talk about it here. It doesn't take into account the material behavior, particle size distributions, and it's really meant to be for the liquid droplets, not the sand, but even for that has a lot of limitations. This is the comparison of API 14E erosion equation versus one famous mechanistic erosion model, which called OCA. So the comparison is versus the steam quality, and you see it's like at the low steam qualities, API 14E is very conservative. And once we have a steam into the system, it's not really safe to use API 14E. So they're really not meant to be considering gas or steam for erosion consideration. So one of the important things we're missing in simple equations like API 14E is they don't take into account what's the material we're using for the tubing and FCDs, and really the behavior of ductile and brittle material is super different. For example, a steel is a ductile material, and we see that the maximum effect of erosion is around 45 degrees. And for brittle material like a tungsten carbide, it's starting to peak up at 70 degrees to 90 degrees. So we don't want the normal exposure of the sand to these materials. And really the reason behind it is for ductile material we call crater growth, and sand is touching things and it starts sweeping the material, and after sometimes the ductile behavior starts shaping these things here, and then we remove the volume and we have sort of a sand dune here. This is the true picture of what's happening, and this is a removed volume. But in brittle material, as I said previously, you don't want the normal exposure, 90 degrees of sand touching the surface. And that's really because the sand coming and impact on the surface and create the cracks and flaws. And by rebouncing, start creating lateral cracks. And once they mingle together, we lose that part of the material. And that's the true picture of what's happening. So that's why we don't want to see 45 degrees, because that's the maximum sweeping on ductile material. And we don't want to be close to anything close to 90 degrees. Mechanistic erosion models such as OCA, which been used in Ashaw package, if calibrated based on the right experimental studies, can predict any sort of experimentals that fit the purpose of the operation. So the square dots are experimental study dots, and the purple curve is what OCA model predict. And the purple curve is the Zhang model, which not being curve fitted properly to the 2005 OCA tests. One of the important things you can see here is the particle size. Before going further, SiO2 is quartz, and that's what the sand is. But you see the particle size is important in any erosion study. So that's why we need to know how the size distribution of the particles are in the reservoir. So this is the different particle size distribution for different facies, McMurray formations. So we're normally talking about McMurray, but McMurray oil sand is different facies. We're dealing with IHS, we're dealing with breccia, we're dealing with clay part of the reservoirs, and a lot of geomodels are built for SAGD operations, which mostly focus on vertical perm of the formation. But one of the important thing is to understand the particle size distribution. Now we're going to talk about it, how to model this in Ashaw package. In previous example, we show how to model developer of SAGD in the Ashaw package. These are the inputs. And we came to the start simulation and we show some of the results in previous example. What we didn't go through was how to do the history match. So this is what you show in the reservoir simulation and what you get at the end. Now you want to do the history match. And in Ashaw package, we're not suggesting to do the huge duration for the history match, because if the model is the right model and the physics is proper for that operation, it has to catch all the dynamics. But the thing you can't catch, because in most cases we don't provide the injection rate, we don't know what the permeability correlations are. The only thing we provide is a gamma ray distribution. So we have to have enough range for the model to do simulation and do the history match for that period. So the thing provided here on the history match bottom here, history match oil rate, is two options. So single variable and multiple variable. In single variable is quite fast, and it's only one variable that been selected in the model is automatic, selected and does the history match on. It's a pretty linear way of history matching. Multiple variable, you can select both because these are different type of variable optimization techniques for the history matching. We mostly suggest to do with a single variable. It didn't work out, then do the multiple, and if it didn't work out, do the single and multiple. But mostly we did like around 50 wells by now, and only exception was one well which was super dynamic, and then we realized the measurements were wrong. We couldn't do the history match with a single variable. So then you, after clicking on a single variable, you put a period that you want to do history matching. So you do come here and you say like 5, and you say 28, for example. And then you click on it on the screen to see the effect. So this blue zone is a zone that you want to do the history match. In this example, I'm showing that's been already history match. It was only one time of the history been history match. And this only zone been history match. And you see the model catch all the dynamics, ups and downs, pre-history match zone and after history match zone. But the thing is different here, because that we want to talk about erosion model, is we see from this point on, which we think that's the onset of erosion, systematically we don't see the history match. We see they are far. We see the rates much higher than what was the oil rate, the field data was. Now we want to see how to model erosion in Ashaw package. So we have to come to the producer and go lower completion. And in lower completion, we have the node, they call it LC, which is lower completion FCD erosion. Once you come over here, there are two libraries available for the user. One is FCD device material. So now we come and say stain on a steel, and then you have different options here. For this case, this is L80, 13 chrome L80, which is a common thing being used. But if you think that you have a tungsten carbide, there are different tungsten carbide material here available for the user. But let's go stainless steel L80. As we previously said, particle size distribution is really important to analyze erosion for any flow control device. In this section, we have to input the particle size distribution along the producer. In the library, we have, for the SAGD operation, we have two types of formation or reservoirs available here. Inclined hydraulic stratification or IHS or mid-McMurray. And for any of these formation types, you have different types of facies. And they are sorted based on size. So rich clay is the finest, as you see here. And if you click on the fluvial dominated IHS, which is the coarsest among all the IHS, you see shown here. So this chart here helps you to see how is the size distribution among the other library material is changing. And the other thing is we have to choose between D10 or D15 that we think that's passed through the sand control system, which is here is a slotted liner. Normally for a slotted liner, a lot of people use D10, but we also put D15 because in some applications, people think that D15 is the part that's passing through the slide liner. There's a guide also provided here to show you what's the definition of D10 and D15. So D15 here means that 15% of the finer portion of the reservoir is passing through the sand control system. By assigning this, you assume along the producer, we have the same type of formation. But this is not the only way of assigning the size distribution. You can come and put the more advanced way of particle size distribution and assign it based on the gamma ray. So you already have a gamma ray inputted for the producer, and you can say here from gamma ray API to 20, which is pretty low. I think that's inclined, and it's very coarse material. And from 20 to 50, it's some sort of silty IHS, and from 50 to very large numbers to the end, it's just rich clay IHS. But for this example, we assume everything is constant along the wellbore, and to just have the better history matching procedure. So then we come to the FCD erosion history matching. We previously history matched the oil rate. So now we come to the FCD erosion. This model is already matched for the erosion as well. So by here, you see this is the before erosion. This is the gray part is just apply history matching to zone here without consideration of any erosion. But you see two purple dots. The first purple dot is this one, and the second one is assigned here. So here the software gives you all the history that been simulated, and you can choose between any of these, the point of onset. So the first one is the onset of erosion, and the second one is the time that you want to assign the history matching of the erosion. So normally you put it towards the end, but not at the end, because you just want to see how the model reacts pre and post history matching. And you see before onset doesn't change anything on the previous model. But after that, because of erosion, you see the O rate is dropping. So this case, onset of erosion is here, and this point is here. So this part we match exactly. But as you see, the model now can capture the physics perfectly, and you see ups and then downs of the oil rates after the onset of erosion. So now we have a model that before this point and after this point, we got pretty nice match. Now we come to the results section. We want to see what the Ashaw software provides for a user to see as a result of erosion. So if we came over here, this shows the ratio between the choking and erosion versus the life of the FCD. This is for a more advanced user to see how things changing, and they may tweak their history matching options for erosion. We're not talking about this portion a lot here, but this is the important chart for most users, is to see this chart shows how the erosion rate is for different portion of the values. This is the MD versus life in the lifetime is changing. As you see here, you see I have more erosion at these points and more erosion at these points and less erosion at these points. And there are two different models here. Red is modified version that consider a steam at the sand phase, and the blue one doesn't consider the sand phase, a steam at the sand phase. So as you see, it's changing. So you can't really base on this say that which FCD is worse. But as you can see how is it changing. So as you go to the end of the life of the FCD, you see this part is a start picking up. The chart underneath is for the people who want to see API 14E type erosion velocity. So the orange is the velocity of the FCD, and the red and greens are limits for the API 14E based on non-corrosive model and corrosive model. The C that previously talked about is changing these two. The occupancy charts is talking about erosion per mass versus the dP of FCD. As you see versus life, it shows how things are changing. As a log scale, you have to be in the linear format. And if you don't see these parts and happening, like they have their dots, which is the outlier, really not following this line, you can change your RS square to fit this part and see how that affecting your history matching. Then we come to the half-life tab. This is an important chart. This is a chart that provides us how long from now on the FCD gonna perform properly. So normally we come after a year after of onset of erosion that we think that's what is start happening, and from that point on you start analyzing the FCDs. So if you come over here, you see these parts showing less half-life, and these are really bad on half-life, and these shows longer half-life. And the half-life, and this, first of all, this y-axis in the years. So for example, this point tells us 6.7 years from now on, this FCD gonna perform quite nicely. But this performance of this one is about half a year or 6 months from this point of the timing, this date from now on, this FCD gonna perform properly. And these are even worse. So these are really dying. So this is really good chart to see how the FCD gonna perform from now on. But as you see, half-life is as a function of erosion that happens till now, and analyze in the future. So it's not constant value, it's changing versus time. But normally if there is a bad part, or if it's a good part, and the bad part, you're going to keep the same because erosion not moving from one point to another point. At last, we just want to go through the overview of the future version. And the future version, we will have the vertical section combined with the horizontal section in the solvent. We will have the vertical section on the gas reservoirs and also the long-term decline on the gas. Hopefully, we will have the SAGD infills building version 5 as well. On the experimental side, we would have the CFD modeling and network modeling for the rel perm. So at the end, I just want to thank everyone who listened to this example.